Awesome. That's for fixing my audio. Gary Berber Jr. back for some more uh, science, physics. I'll do some cosmology today. I'll actually do some reading of my cosmology textbook, which you can see here. So it is a graduate level cosmology book. I'll go through it and see what we find in chapter 2. So I'll be starting from chapter 2. And let me see what's up with this. So I think it's different. I know it's different about my pad. That's what it is. Should do it. So the textbook is Bowman. It's apparently a popular textbook of cosmology and as far as graduate astronomy goes. Hmm. So we'll be looking at that book. Already started reading it, so we'll continue from where I was with in chapter 2 and see how far I go. I'll go until I guess the top of the hour. Let me know if you have any questions, those that pop in. Took off on a break, by the way. So longer break than anticipated, but a much needed break. So got a little bit of rest and relaxation and played some games. So I'll try to have a more structured or scheduled break next time. Let me see if I can do a bit more to make sure the book is fully visible. Think about it is I'm going to give us a little bit more space on that side. And a little less space on that side. And that seems good. So we'll go ahead and get started. I'll start with the end of section, what is this, 2.1.1, and work from there to see how it goes. Spatial homogeneity and isotropy of the universe mean that it can be represented by a time-ordered sequence of three-dimensional spatial slices, each of which is homogeneous and isotropic. It's given us figure 2.1. These are slices of the universe, each of which is homogeneous and isotropic. So the homogeneous means that no matter which point you place your focus of observation from, everything looks the same, and isotropic means it looks the same in every direction. The four-dimensional line element can thus be written as says 2.1.1 continued. DL squared is gamma ij x to the xk dx I dx j. So it's been a while, but some of you may remember the Einstein convention where duplicated indices are summed over if one is up and one is down. So there's a ij down here and an ij up there. So that means that this is the same thing as gamma OO x k dx squared. I guess I should say dt squared. I'll just say dAO squared, dxO squared plus gamma 1 x k plus at least xO squared dx1 squared onto d4. At least 3. The fourth term is 3 since it's starting at 0. So that's a sum. It's interesting. It seems like the okay. So the AT is on the spatial position. You can say our C squared. Hold up. We need to remove the extra text. There we go. So we can see how the BT squared part has negative C squared on it. And each of the components of the spatial component has A squared on it, which is the scale factor, as it says next. So line and AT is the scale factor, which describes the expansion of the universe. We will first determine the allowed form of the spatial metric, gamma ij, and then discuss how the evolution of the scale factor is related to the matter content of the universe. Right? Homogeneous and isotropic free spaces must have constant intrinsic curvature because it would oh, there are then only 3 options. The curvature of the spatial slice can be 0, positive, or negative. Let us determine the metric for each case. All right, so we can see the 3 here, the flat, spherical, and hyperbolic universe. The space-time of the universe can be foliated into flat, spherical, or positively curved, or hyperbolic, negatively curved spatial hypersurfaces. And I may increase the size of this a bit. I may need to adjust my little filter on it. Let me make the text a little bit bigger. No, seems all right. Would have the black hole background, which is cool. I think that works out. You can't see the book completely, but the idea is to see the handwriting more so. All right. So flat. Pick something out my pocket real fast. That the simplest possibility is the three-dimensional Euclidean space E3. This is the space in which parallel lines do not intersect. Its line element is dl squared equals d x vector squared, which equals the Kronecker delta ij dx I dx j, which is clearly invariant under spatial translations. So xi to xi plus ai in rotations xi to ri k xk, with Kronecker delta ij ri k ril equals Kronecker delta kl. All right. Spherical space, positive curvature. On such a space, parallel lines will eventually meet. So flat, you have parallel lines, like they'll never meet. They remain parallel. Spherical, parallel lines converge. The geometry can be represented as a three-sphere S3 embedded in four-dimensional Euclidean space E4. So we have dl squared equals dx squared plus du squared, and x squared plus u squared equals ro squared. That's 210, where all O is the radius of the sphere. Homogeneity and isotropy on the surface of the three-sphere are inherited from the symmetry of the line element under four-dimensional rotations. Right? I'm sure some of this will become more clear as I go along. Parallel lines. We have hyperbolic. Free space with constant negative curvature. In such a space, parallel lines diverge. This geometry can be represented as the hyperboloid A3 embedded in four-dimensional Lorentzian space R1, 3. So here, dl squared equals dx squared minus the u squared. You notice it's a minus rather than a plus from before. And x squared minus u squared equals negative ro squared, 2.11. And here, parallel lines diverge. The ro squared is greater than 0. There's a constant determining the curvature of the hyperboloid. Homogeneity and isotropy of the induced geometry on the hyperboloid are inherited from the symmetry of the line element under four-dimensional pseudo-rotations, i.e. Lorentz transformations, but U plane the line elements of the spherical and hyperbolic cases can be combined as dl squared equals dx squared plus minus du squared, and x squared plus minus u squared equals plus minus ro squared. This is 2.12. Just notice that even though I wrote it, but there's a positive for each of these in the spherical case. In the hyperbolic case, there's a minus for the du, a minus for the r, and a minus for the u squared. The differential of the embedding condition gives u du equals minus plus dx dot dx, x dot dx, so that we can eliminate the dependence on the auxiliary coordinates u from the line element. Like that is replaced du with the dot product thing, but it's saying u du equals minus plus x dot dx. Thus, dl squared equals dx squared plus minus x dot dx squared over r squared minus plus x. It's 2.13. In the moment I shall refill my water cup. I'll be right back. So there's a lot of intricate math in cosmology. Apparently, cosmology is highly um, filled with general relativity. So let's see how this goes. Finally, we can unify 2.13 with the Euclidean line element 0.9 by writing, if you have the dl squared equals dx squared, so now they're removing the plus. Dl squared equals dx squared plus 3. plus k x dot dx squared follows minus k x squared, for k is 0 for a cubed, plus 1 for s cubed, and negative 1 for h cubed. So we can see how they combine the three of these. There's a negative for hyperbolic, a plus for spherical, and there is no du for flat. It's a convenient way to do it. Pause for a moment. I'll be right back. I may actually save a little time and refer to some notes I made before. So the book right here is on spherical polar coordinates. And it's in spherical polar coordinates using dx squared equals dr squared plus r squared d theta squared plus sine squared theta d squared phi, which should be r is the distance from the origin. This is the polar angle, in physics, and this is the azimuthal angle in physics. So plugging this in, we get dl squared is that, which they denote this entire last part as d omega squared. And it talks about the Robertson-Walker metric. So situating 2.16 into 2.8, we obtain the Robertson-Walker metric. In polar coordinates, ds squared equals minus c squared dt squared plus a squared t times, all in brackets, dr squared over 1 minus kr squared over r naught squared plus r squared d omega squared, and again d omega squared is this entire thing. Equation 2.17, which is sometimes called the Friedmann-Robertson-Walker metric. The symmetries of the universe have reduced the 10 independent components of the space-time metric g mu v to a single function of time, the scale factor at, and a constant, the curvature scale r naught. So this is the scale factor, and this is the curvature scale, which should be the radius of the circle, which, I mean, it seems, if we're talking about the universe, it'll be 14 billion light years or whatever it is. Not sure about that though. It's also said that there's no real center to the universe, but that still doesn't make sense to me, given the expansion, but space itself is expanding. I know that's something I could perhaps ask my professor about. First of all, the line element 217 has a rescaling symmetry with gamma. This means that the geometry of the spacetime stays the same if we simultaneously rescale AR and R naught by a constant lambda. So everything is getting farther away from each other, but the overall shape of the universe is the same. We can use this freedom to set the scale factor today at t equals t naught to be unity, a t naught equals 0. The scale r naught is then the physical curvature scale today, justifying the use of the subscript. And we can see here how the co-moving distance, which is the distance of the, based upon the actual point in the universe relative to other points. But the physical distance, the physical coordinate distance changes as the expansion occurs. So I drew it here just like I have it in the book there. We have the co-moving distance 0, 0 to 1, 0. That stays the same. So the, position in space relative to another position in space, given the expansion of the universe, will remain the same. But the physical distance between the two expands. The physical distance, on the other hand, grows in proportion to the scale factor A of t. The physical is how the physical position changes over time, and R is a function of AT, or physical. So dA dt is d dt of R, going to be a dA dt r plus a dr dt, the chain rule. Then we have the Hubble flow, how the scale factor changes times the physical distance. Then we have the V peculiar, which is AT is remaining the same in that local space, but the position itself within that space is changing. We have the Hubble parameter, which is the change in the parameter, the scale factor divided by the scale factor. The complicated, to get at the bottom sentence, the complicated GRR component of 217, which is the Robertson-Walker metric number 217, can sometimes be inconvenient. In that case, we may redefine the radial coordinate, the psi, as dr squared over 1 minus kr squared slash r naught squared, such that ds squared equals negative c dt squared plus at squared d psi squared plus sk squared psi of psi as a function of psi d omega squared 2.21. We can see now that sk of psi has the negative zero or positive term to bring in the different types of universes. Note that for a flat universe, k equals 0, there's no distinction between r and psi. The form of the metric in 2.21 will be useful when we define observable distances in sections 2.2.3. Finally, it is often helpful to introduce informal time. D now forget the name of that symbol. D fancy n bt over 8 of p. So that 2.21 becomes that. And welcome who's watching. Let me know if you have any questions or comments in the live chat. I am checking that out. We see that the metric has now factorized into a static part and a time-dependent conformal factor, a fancy n. This form of the metric is particularly convenient for studying the propagation of light, for which ds squared equals 0. We have to think about that. Ds squared equals 0 for propagating light. As we will see in section 2.3.6, going to conformal time will also be a useful change of variables to obtain certain exact solutions to the Einstein equations. Now we have 2.2, kinematics. Having found the metric of the expanding universe, we now want to determine how particles evolve in this spacetime. It is an essential feature of general relativity that freely falling particles in a curved spacetime move along geodesics. I will first introduce some basic facts about geodesic motion in GR, and then apply it to the Robertson-Walker spacetime. More details are given in Appendix A. Let's spend some time on Appendix A. 2.2.1 Geodesics. Before we study how particles evolve in a FRW spacetime, let us first look at the simpler problem of a few particles in two-dimensional Euclidean space. curvilinear coordinates. In the absence of any forces, Newton's law simply read acceleration is zero, which in Cartesian coordinates xi equals xy becomes, I mean, that's simple enough. Acceleration is zero. In a general coordinate system, however, the acceleration equals zero does not have to imply the acceleration of one particular um, factor or direction is zero. And welcome who's joining. If you have any questions or comments, let me know in the live chat. I am looking at that. But I do remember Professor mentioning this, how the example he gave is if we have a coordinate system that's Cartesian, but we have a straight line, but the line is rendered in polar coordinates. You could have psi dot changing, and you could have the dot changing, even though r equals zero. Let me illustrate this explicitly for the polar coordinates r, phi. So example, and welcome who's joining. Let me know if you have any questions or comments. Back from winter break. You should expect to see me every Saturday. Maybe I'll take another shorter break in summer, but I'll make sure to keep the break shorter next time. Using x equals r cosine phi and y equals r sine phi. The equations of motion in 2.25 imply is interesting. Because the equations of motion is going to be x double dot equals d dt. That's going to be a long derivative, isn't it? But all it did was just basically take the second derivative of x in that form and then square it. And the same thing with y and square it. Solving this for r dot and phi dot, we have r double dot equals r phi dot squared, and phi double dot equals 2 over r times r dot phi dot. You see that r double dot equals not 0 and phi double dot equals not 0, except in the special case that phi dot equals 0. Okay, so it was r and phi, not theta. The reason is simply that in polar coordinates, the basis vectors r and phi vary in the plane. To keep x double dot equals 0, the coordinates must then satisfy 2.27. So I showed that the equations of motion 2.27 can be derived from the Lagrangian of the free particle, where m is the mass of the particle. All right. Welcome who's joining. Let me know if you have any questions or comments in the section. Back from winter break. To derive the equations of motion in an arbitrary coordinate system with metric Gij does not equal the Kronecker delta, you start from the Lagrangian. L equals m over 2 G double I x to the k xi dot and xj dot. That's a sum. I don't see where, if I remember right, the Lagrangian is the kinetic energy minus the potential energy. I guess they're saying that potential energy is zero. Substituting this into the Euler Lagrange equation, we find d squared xi plus dt squared equals the Christoffel symbol, dx e over t dx b over t. We got, all right? I'll write that down. The Christoffel symbol, I, A, B, is defined as 1/2 G, I, J, partial A, G, J, B, plus partial B, G, J, A, minus partial J, G, A, B. And we have welcome who's joining. Let me know if you have any questions or comments. I am watching the live chat. I'll be on for about 10 more minutes. And partial J is defined as partial over partial X I. This is 2.31. In the special case Gij diagonal, 1 r squared, the non-vanity components of the Christoffel symbol are gamma phi equals negative r, and gamma phi or phi equals phi r equals r inverse, and 230 leads to 2.27. Derivation of Euler Lagrange equation is d dt partial L over partial xik equals partial L over partial xk. Normally, at least in my experience, is written as minus the other side equals 0. It still gives you the same thing. It looks like we might be doing Euler Lagrange in this class, which I'm not upset about. Since the mass m will cancel on both sides, we would not write it explicitly. The left-hand side of 2.32 then becomes that, while the right-hand side is that. Combining 2.33 and 2.34 then gives, multiplying both sides by DLK and using GOK, GKI equals delta LI, we get produce the desired result, 230. Interesting. So the Christoffel symbol comes from working the Euler Lagrange equation. Okay. So the Christoffel symbol is the result of the equations of motion from the Euler Lagrange. Maybe I'll do that next week. Derive the Christoffel symbol. I have to figure out how that's done. Look at this very closely. I notice this book seems to skip a lot of steps. The equation of motion of a massive particle in general relativity will take a similar form as 230. However, in this case, the term involving the Christoffel symbol cannot be removed by going to Cartesian coordinates, but is a physical manifestation of the space-time curve space-time. For massive particles, a geodesic is the time-like curve x mu of proper time, which extremizes the proper time change in t between 2 points in the space-time. In our conventions, proper time is defined by the relation CD tau squared equals negative ds squared. A relativistic action of a massive particle is S equals negative mc squared integral d tau. So extremizing the proper time between two events is equivalent to extremizing the action. Welcome who's joining. Let me know if you have any questions or comments. I'll be on for just under another 10 minutes. Where the Christoffel symbol is that. Well, I think I skipped. Massive particles. In Appendix A, I show that this extremal path satisfies the following geodesic equation. So this geodesic is for massive particles, and by the way, a geodesic is basically the path a particle will take in curved space-time, which is why this section must be called curved space-time. So the geodesic equation is d squared x mu over d tau squared, which equals negative Christoffel symbol a b dx alpha over d tau dx beta over d tau. 2.3. Right. Seems like a good place to end. So I'll hop into this new section here. And what I may do next week is actually look at this Christoffel symbol because it comes up a lot. I see it a lot. We see it from all of the Lagrange equations right here. So 230, hold up. What was it at? 231. See how they get the Christoffel symbol from the fine Euler Lagrange. But it's interesting. So I may actually look at that next week and derive that since the Christoffel symbol comes up so much in cosmology. See, look at it. See it right there? It's right here. It should pop up again like he's scrolling. Oh, talking about supernovas. Oh, I'll be utilizing supernovas in my research to get cosmic distances. Okay. That's why I knew, let's say I necessarily like cosmology, but it's related to my research. I like stars, but the application of my research will be cosmology. So even though I hate cosmology, not because I can say I hate it, but I think it's more mathy than I like. Put it that way, as you all are seeing. but learning I shall. And look at it. See it popping up. So next week I'll derive the Christoffel symbol, and maybe I'll see about doing something else as well. The three classes I'm taking right now, hold up, are Prodigy, uh, statistical mechanics, and methods of theoretical physics. So I'll be talking about those things this semester. I think over the summer I'll finish my uh, what is it, foundations class, and let's see what we take next semester. Pop, I was supposed to fill out a form for that. I think I forgot to. So let's see how pick with classes, but that will work out. But thank everybody who joined. Thank you for joining. Let me know if you have any questions or comments in the comment section of this video. I'll probably do a little bit of editing, just getting back into it from winter break. So I had a few false starts, and I'll be back next week. We'll keep it going the semester. Have a good one.